Hi, in this video, I'll be showing you applications of integration. Since in the previous videos, we went through what is integration, how do we find the antiderivatives of common functions, and we went through also techniques of integration. Review them before following on with this one because you'll be using those to evaluate what are definite integrals. And to evaluate, so we need to find its antiderivative. So a good and strong foundation of what we have already learned will help you now in understanding and applying the techniques to solving problems. So the most common form of application for integration is of course finding the area of a region bounded between two graphs. We already know that integrating a function will give you the area between the graph and the axis. And so if you want to find area of region bounded between the graphs, then it's just taking the area of one. So let's say fx is above gx and minus away the area below, which is gx from a to b. And then you can combine them because they are both the same limits. So now it's a to b of fx minus gx, which is this formula over here. And so this gives you the area bounded between two graphs in the direction of the x-axis. Why do I say in the direction of the x-axis? You will understand why later on. For example, you have an area enclosed by 2x minus x squared and x squared. So you want to know the region of area here. Well, you just need to take the area of the top graph minus away the bottom one, which you can easily find over here. And so the area is just integrating 2x minus 2x squared. Of course, 2x becomes x squared, and then 2x squared is just 2 over 3x cubed. And then you sub in 1 and 0 respectively. And that's how you get 1/3. Now, let's say instead of doing it with respect to x, you want to use the curves with respect to y, meaning that now you want to integrate the area between the graph and the y-axis. So it's like this. So you need to take the one on the right minus the one on the left. So now it's the red one minus the blue one. In the earlier, when you treat them with respect to x, the blue one created a greater area compared to the red because it's above the red. But now you want to do it with respect to y. You want to take the one on the right, which is now red. And so you treat x as a function of y, and you find the length formula, which is square root x minus 1 minus square root 1 minus x, 1 minus y, I mean. And then integrating to find the area is just integrating the length formula with respect to y from the limits of 0 to 1. And you get the same result because they are the same area. So you can either do it with respect to x or with respect to y. It doesn't really matter as long as you're able to find the region correctly and you're able to identify it correctly. So this is of course one of the most common forms of application, which is to find the area. And basically everything else is something like finding the area, but now we are because what we want when we find the area is that we use the length function. And so when we want now another application, now we'll move on, is the calculating the volume. And to calculate the volume, it is basically integrating the area function. So you can see how area was integrating the length function, and you capture that idea and generalize that notion. When you want to calculate the volume, you really be integrating the cross-sectional area function. Because if you think about it, while I will not prove this, you can actually just prove this using limits from first principles, but I'd rather give you an intuitive understanding. You got a base area here, and you have it's like a cylinder, and you keep stacking each of these areas higher and higher, so it's h height. So you're basically taking like infinite number of planes, and then so that is like you're integrating it from 0 to h. and that's the limits from A to B, and you're just taking at each height what is the area, and so the volume is integrating the area cross-sectional area function. So let's take a look at an example to illustrate our point. For example, I have a pyramid 3 meters high and has a square base. There's 3 meters on its side. We can draw it with respect to the y or x-axis. In this case, the textbook has drawn it with respect to x. So our base area is at a mark of x equals to 3. And y is, the length of it is 3. So this is like 1.5 up and 1.5 down. Similarly, is minus 1.5 and this is 1.5 up. And then they say the height is 3 meters, so that's why it's a distance 3 away from the origin. So the cross-sectional area is this square over here with, let's say, at the point x. And so at any cross-sectional area, the area is just x squared. So you're really integrating from 0 to 3 of this x squared, which just becomes x cubed over 3, and then you just sub in x 3 cubed over 3 minus 0 cubed over 3, which is 9. And so you can see it's fairly easy when the problem is easy to integrate. Of course, the problem could be very difficult, and actually you can just integrate any function as long as you are able to find its area function. So example 2 is a more complicated one, but the idea is the same. So now you have a right cylinder, but it's like slanted. It doesn't really matter because you want to draw the cross-sectional area perpendicular again to the axis, so that when you integrate them, it'll be the whole volume. And so you realize that at each time, each cross-sectional area is the height of this rectangle times the width. And so the height in this case is x, and the width is 2 square root 9 minus x squared. And you can simplify it to 2x square root 9 minus x. And so as the rectangles run from 0 to 3, you're basically just integrating this area function from 0 to 3, and you can get the result over here. So really you want to practice more on this to better understand how to find the cross-sectional area. It may not always be as straightforward as saying the length, because the length one you just need to take the top function minus the bottom with respect to x, or the right minus the left with respect to y. But for volume, you really need to pay attention to what is the area function. And once you get that, it's very simple. You just apply your techniques of integration, which we have learned in previous videos, and you'll get it. So I like to stress again the importance of practicing so that you can be familiarized with the types of question that requires you to solve using integration. And with that idea of cross-sectional area, mathematicians have come up with another way. Instead of always drawing these squares or rectangles, which is very fixed, mathematicians have wondered, how about, let's say you have a sphere, and how are you going to be able to chop it up into cross-sectional areas that is easy to integrate? Well, what they have come up with is that you already know that the sphere can be approximated with right cylinders, so you can chop up into like these circles if you look from it from this angle. And what it means is that for each cylinder, what is the volume? Well, it's pi r squared h at each point. And so you will be able to show that the dv dx is actually just pi bracket 1 minus x squared. And so the volume of the unit sphere is integrating this function from minus 1 to 1. And you get the same result as you always been known as 4/3 pi. And so what we take this idea of approximating a sphere with circular cylinders to realizing that any function that you rotate about the axis, you're able to find its volume by integrating from a to b of pi bracket fx squared dx. So the idea, this is known as the disk method for calculating volume of revolution, and that's because this cylinder has a radius of fx. The dx serves as the height over here, so it's a very small change, that's why it's dx. Then you integrate from a to b, and with that you'll calculate the volume of this right cylinder over here, this very thin right cylinder, and then when you integrate it all, you're just adding all this sum together, and that's how you get the solid of revolution. So in the previous examples, when we calculate the volume of something, it's a more rigid system where you're just actually taking the same idea, but instead each time you approximate at each point with like a cross-sectional area. So this is not really a rotation around any axis, it's really just a solid, and then you find it from the basic understanding. But say you got a function and now you want to rotate it and you want to calculate the solid of the volume for this solid of revolution, then you can use this method called the disk method to find it. So it's just pi r squared h. In this case, our h is with respect to what, and this fx is our r. So usually the trick is, if you have a function here, you just draw at a random point x and see what is the fx, so, and that will be your r. So let's take an example so that we can practice. So consider the region between square root x and the x-axis. So this is the region we're looking at, and we rotate it about the x-axis. Then the cross-sectional area is just pi r squared, because it's a circle, and that is just pi x. And so the volume is integrating this dx, so it's pi over 2. And you can see it's really capturing the idea now that our cross-sectional areas are all circles instead of squares or any other functions. And that's why it's pi fx squared. Similarly, like how in the when we calculated area, we can do it with respect to x or with respect to y. When we are rotating about the y-axis, we also can just do the same thing. So we need to express our original function in terms of x in terms of y now, so that when we calculate the area function is pi gy squared, where g and is the inverse of f. So this gy is y cubed, cube root of y. So pi cube root of y squared is pi times y 2/3. And so when you integrate it, raise to the power by 1, divide by the power, and you get the following expression. I hope it's clear to you. We'll try out another question for you to better familiarize yourself. But this time, I'll introduce a new method of solving the volume, which is really an extension of what we have learned. In this case now, your solid of revolution is bounded between, it is a region bounded by two graphs. So like the original, when you have an area and it's just one, you just integrate normally. But if there's two, you need to minus. And that's basically the same idea. So now this is called the washer method, and it's because if you look from this direction now, imagine you have one circle and then you have a graph here that creates a smaller circle, and so it's a bigger circle and this is smaller, and your volume is this cross-sectional area now instead of the whole circle. So how do we calculate this area? It's just taking the area of the big circle minus away the small one, and that's why it is taking the big volume minus away the inside volume. And we see that when we simplify, it's pi fx squared minus gx squared. And the most common mistake is that everyone thinks it's fx minus gx squared. Like you take one length minus away and then it's squared. But the area formula doesn't work like that, and fx squared minus gx squared is not the same as fx minus gx whole thing squared. And so this is wrong, and you must remember that if you want to go back to first principle, it's really just taking the bigger volume minus away the smaller. So if you don't want to remember this compact formula, just take the bigger one minus the smaller, and then you just solve it out in two separate integrals, and you will get the result that you want. So let's take a look at this example where now our region is bounded between the graphs, so we need to use the washer method. We want to rotate about the y-axis. So this graph below here, which is y equals to x squared, when we rotate about the y-axis, it forms this frustum. And then this line will form a cone that we have to delete away. So we just need to take the first volume minus away the second volume. In which case, it means that it's ry squared, capital ry squared minus away mini ry squared. So it's square root y squared minus y over 2 squared, which then is just a simple polynomial which you can integrate easily. Of course, not always will it be such an easy function, but in this case, we use an easy example to illustrate our point of what is this method, which is basically just how the volume of revolution formula is created, and the washer is an extension of that because you just take one volume minus over the other. So do practice more, and I've come to the end of this video. So we'll see more application of integration in the next video, and I'll catch you again. Thank you for listening, and I hope you have enjoyed it.